Hey, everyone. Great to see you all as always. Give just a minute here for everybody to make their way in. All right. Anybody have any questions? Anything you want more information about or? No? All right. Let's go ahead and get started then. Thank you for being on time. I do appreciate that very much. All right. You can see that little frying pan there cooking up the earth, cooking up pieces of the earth, actually. So last week, you guys you finished the rock unit and you started the unit about tectonic plates. If you are keeping with the due dates, which most of you are doing a really good job with. Some of you are even ahead of the due dates. So what does that mean when I say plate tectonics? What do I mean? What exactly are plate tectonics? Anybody? Well, it's a good thing you're here today then, because we are going to learn all about plate tectonics today. I do have a couple jokes for you first, though. So let's have some jokes, and then we will get started. So what did one tectonic plate say to the other when they crashed together? Sorry, my fault. My fault, because this is a fault line. In between the two is called a fault line. So sorry,
I can't see your screen.
You guys can't see my screen? Can anybody see it?
I can.
I can see it.
Okay, Isaac, you might want to go out and come back in. Maybe it's a glitch with your computer. All right, sometimes that works. All right, good. If that ever doesn't, if it ever happens, let me know. Because sometimes I do forget to share it, or I think I've shared it and I didn't. All right, here's your next joke. Why aren't tectonic plates allowed in the mattress store? Because they make the bed rock. And what is a volcano? A volcano is just a mountain with hiccups. And for the cat lovers out there, the world is a cat playing with Australia. You see that little right there? We can do the outline of it. Of course, you could turn into just about any animal, but I thought that was cute. The world is a cat playing with Australia. All right, let's do some review now. Let's review the structure of the earth. So what is this on the very outside where the land and the water is? What do we call that part of the earth? Helena?
Crust.
That is the crust. Absolutely. What's right under the crust? Maisie?
The outer crust.
So the crust does have layers. There's actually a lot of different layers of the earth, but we focus on 4 major ones in our course. So what's the major one that's right underneath the crust? Henry?
The mantle.
Yep, it is the mantle. The mantle. Remember that the crust is solid rock, but as we get deeper, it gets hotter. So the mantle is so hot that the rocks in the mantle partially melt. They become what we call molten or magma. All right, so what's right below the mantle? Aisha?
The outer core.
The outer core, right. So is the outer core hotter or cooler than the mantle?
Cooler.
It actually is cooler. Isn't that funny? And then what is below the outer core? Jasmine?
The inner core.
The inner core. Excellent. All right. Now take a look at this. Stop and think for just a minute about all the heat that's inside the earth and in the magma. So magma doesn't just sit there calmly. It actually moves around a lot inside the earth. Now we can't feel that with our feet when we're walking on the earth. We don't feel that movement, but it's there. Right underneath the crust, we got this mantle, and it is moving in this amazing circular way. So remember, we learned that the interior of the earth, the inside of the earth is hot. It's hot for two. So we'll talk about that, Henry. That's a good question. We'll talk about that in a second here. It has to do with chemical reactions that are happening there. Now, remember that we learned that the interior of the earth is hot for two reasons. First, when the earth formed, it was very hot. So at the very beginning, it was very hot. Then as it started to cool down a little bit, there was a major collision that caused the earth to heat up even more. So they think that something really huge smashed into the earth and broke off a giant chunk of it. And both of those chunks then became molten, and things sort of settled in. The heavier elements sank to the middle, the lighter elements stayed on the outside. Those two pieces that the earth broke into were what we now know as the earth and the moon. The moon was one of those pieces. So that major collision caused a lot of heat. That's one reason that the interior of the earth is hot. The heavier elements sank down to the core. The lighter elements like oxygen, hydrogen, they stayed up near the surface. Now, over time, some of that energy began escaping out into the earth, and that allowed the earth to cool. And eventually the earth cooled enough that liquid water could form on the surface. Now that thermal energy, that energy of particles moving, that heat, if you will, escaped really slowly. And it's still escaping. So some of that initial thermal energy from when the earth formed is still there. It's still inside. So Earth's molten stage was in the early formation when elements sank. That left that thin layer of materials on the surface that is now called the crust. That should say now. The majority of the mass of the earth lies down below the crust. Now, a bigger reason that it's so hot inside the earth is because those heavy atoms went deep into the earth. Remember, when it got really hot, the heavy things moved to the center. So those heavy atoms move deep into the center of the earth. We have to remember what atoms are. So let's review atoms quickly. So first of all, we have these things with negative sign flying around the outside of an atom. What are they called? The negative things that go around the outside of the atom. Helena.
Electrons.
They're called electrons. Excellent. What are the positive things that are inside the atom called? Maisie.
I forgot what it's called.
Okay. Anybody remember what the positive ones are called? They both start with a P. Positive. Drake.
Neutrons. Oh, wait,
Sorry.
no.
The positive ones start with a P. Go ahead, Drake.
Protons.
They are protons. Protons are positive. Then we have the neutral ones that don't have any charge at all. There's no sign in them. There's no positive, no negative. Those are called neutrons. Now, in the center here, these protons and neutrons are clumped together. That's the part that we call the nucleus. So there are 6 protons and 6 neutrons in the nucleus of a regular carbon atom. All right. All the atoms are the same. They just have different numbers of protons, neutrons, and electrons. Here's the thing that's really crazy. Every proton in the universe is the same. Every neutron in the universe is the same. Every electron is the same. Now, when you get to advanced physics, you'll learn that there's tiny differences, but for all practical purposes, they're the same. What makes one thing different from another? What makes like gold different than oxygen is just how many protons there are. Right? All right. Now, atoms also weigh different amounts. They have different what we call masses. So on Earth, you can think of mass and weight as being about the same thing. Mass is how many particles there are. Weight is how much gravity is affecting it. So you would have the same mass no matter where you went in the universe, but you wouldn't weigh the same if you stood on the moon as you do here. So the mass tells us the size of the atom, how much matter there is in the atom. And that mass increases as you go up the periodic table. So look at this. Hydrogen is a 1. That means it has 1 proton. Beryllium has a 4. That means it has 4 protons. The atomic mass number is down here at the bottom. So beryllium is 9.012. That atomic mass number tells us how many protons and neutrons there are in the nucleus of the atom. The atomic number is usually the number of protons that are there in the element's nucleus, while the atomic mass number is the protons and neutrons together. So let's zoom in on a couple of these. Let's look at hydrogen and uranium. Now, hydrogen, it's really little, right? It has only one proton. What's the atomic weight of hydrogen? What's the atomic weight? Remember where I told you find the atomic weight? Why don't two squares have anything in? Oh, you mean back here? Yeah, that's a really good question, Henry. Anybody know that? Why are these two blank? Helena.
Because it like drops down to the bottom.
These right here, 57 to 71, 57 to 71. They go right in there. And then 89 is here, and then 103 is here. So all of these should go in there. But we put them in there so that we put them at the bottom so the periodic table doesn't look like this. We can fit it all on one small page if we take these out and put them below. And then we have that space right there that shows us that those are supposed to go right there. Excellent question. All right, so taking a look again at the hydrogen. So let's zoom in on this hydrogen right here. So right here, this underneath there, I don't know if you guys can really see that. It's 1.008, lithium is 6.941. Now on this one, on the next page, the hydrogen, it's a little bit different. It's 1.008 is right there. What is the atomic weight of uranium? The atomic weight is the protons and the neutrons together. So the atomic number right here is just the protons. The atomic weight is how much they weigh together, 238.03. Now, hydrogen is the lightest. It's the smallest atom. One of the heaviest naturally occurring ones is uranium. Can you see how uranium is a lot heavier than hydrogen? It's got a lot more protons, and it has a lot more protons and neutrons together, adding up to make this number right here. Yeah, excellent. So look at hydrogen again. That's right here. Now find uranium. I'll give you a hint. It's a U, and it's in the bottom number, or bottom row, sorry, the bottom row. You see uranium? Here it is right here. This is uranium right there. So its atomic number is 92. That means it has 92 protons. Its atomic weight is 238.029. That's how many protons and neutrons it has. All right, now once again, we pull these out like that so it doesn't look like that. That's an important thing to remember. That's what those are for down there. All right, so here's one of the problems. We've got all these elements. Well, the bigger an element gets, in other words, the farther down on the periodic table, so these are big ones down here, these are small ones up here, the bigger it gets, the more protons it has in its nucleus, the more unstable it becomes. So it actually can break down into smaller atoms, and it does so in a process called radioactivity. Have you ever guys heard of something being radioactive? Something that's radioactive is likely to break down into smaller pieces. And when it does, when an atom breaks down into smaller pieces, it releases a tremendous amount of thermal energy. And that's the other part of why it's so hot inside the Earth. So remember, there are a lot of those heavy elements down near the core because of that big collision. Since those heavy elements can break down through radioactivity, there's still a lot of thermal energy that's being released deep in the core all the time. In fact, most of the heat that's inside the Earth is caused by this radioactivity, and it's still going on most of the time. Now, here's an example, looking again at uranium, how it breaks down. So uranium is a big, I've mostly heard of stuff being radioactive. Yeah, and well, yeah, radioactive. Well, that's not exactly, those are not exactly factual in the way that they're radioactive, but it gives you the idea. When something is radioactive, it means it can break down into more parts. And radioactivity releases a ton of energy. So that's what they're doing in the superheroes. They're capping on the energy that happens in this radioactive decay. So take a look at uranium. We start here with uranium. Uranium has what's called a half-life of 4.4 billion years. So uranium can break down very quickly into radium, which is another element. They're both metals. It will decay. It'll break down into radium. And then very quickly, radium breaks down into radon, which breaks down into polonium, which finally decays into lead, and then bismuth, and then another version of polonium, and then another version of lead. And finally, after all this, we get to a stable element, lead. Just plain lead with 206 protons is stable. Every one of these arrows right here is a release of energy. A lot of energy is released when uranium breaks down, and that energy heats up the inside of the earth. All right, so last week we talked about how when the sun shines on the earth, it heats the earth unevenly. We talked about how hot air goes up and then cool air rushes in to take its place, and that makes wind. Well, yeah, radioactivity is not good for people. Yeah, it can do damage to our cells, living things. It can do damage to. Yeah. What are A's and B's for? Henry, those are great questions. This means beta, and the A means alpha. So it's an alpha form of lead. Once again, you're looking at more advanced chemistry here than we need to worry about right now. I just want you to see how many steps there are, and that in each one of these steps, to go from the beta form of bismuth, which has 214 protons, to the beta form of polonium, which also has 214 protons, we're releasing a lot of energy. That's just what I want to see here. Okay, so air goes up, hot air rises, cool air comes in to take its place, and we get this wind, this circular current that we call convection. Well, that same exact thing happens with liquids. We have convection in liquids. Now, to understand what the word convection is, you have to understand what the word fluid means. So what do you think it means? What do you hear when you think fluid? Valerie.
When I think fluid, I usually think of water, but I also think of kind of like a liquid that can move, or
Yep.
fluid like an emotion almost.
Like an emotion?
Like, you know how I don't know, never mind. But yeah,
No, go
usually I just
ahead.
think of water. When I think fluid, I think like I don't know, like you know how like sometimes it look like something can look like it's moving very like fluid almost?
Yeah.
Like smooth.
Yeah. So that's the second part of your answer is really a good definition of what a fluid is. And water is a good example of what a fluid is. A fluid is anything that can flow. So flow means that movement like that. So water can flow. Water is a fluid. But guess what else can flow? Air. So air is a fluid. It's not liquid, but it is fluid because it can flow. All right, so flow means just basically to go from one place to another in a steady stream. So since air can flow, it's considered a fluid, but it's not a liquid. Those two things are different from one another. Drake.
So cars can sort of like flow from one place to another?
I don't think I would consider the way a car moves being a fluid. No, that would be a mechanical movement that would be different, but you're on the right track. You're thinking, and I love that. So a flow, something that can flow, is something that can go in a steady stream from one place to another. And fluids are things that they don't have any fixed shape, right? They're going to be able to change their shape pretty easily. All right, now back to convection. Take a look at this picture. What's flowing here? What is the fluid here? Yeah, Maisie, like kind of like a boat on the water, like the water is flowing, carrying the boat with it. Isaac,
The water is flowing around
Yeah.
to get the hot water up and the water down.
excellent,
As
excellent.
heat
So,
rises.
yeah, yep. So we have water in the teapot moving. There is conduction happening where the flame contacts the pot, it's getting really hot. The hot water inside the teapot rises up and cooler water sinks in to take its place. As soon as that hot water gets away from the heat source, away from this, it starts cooling down and it starts to go down. And that is a convection current. Now, when at least one substance involved in the thermal energy transfer or the movement of heat can flow, we call it convection. That's how we say that energy is moving, by convection. Now, convection can also occur between a solid and a fluid, like I'm taking my hand through the air right now. That's convection that's happening because one of those things is fluid, the air is fluid. It can also occur between two fluids, like water and air. So enormous amounts of convection occur between the ocean and the air above it. So just remember, hot things go up, cool things come down. And when they do that, they make this circular pattern called a convection current. Now, down in the mantle, you've also got, remember, in the inner core, it's going to be really hot. Convection is going to happen in the mantle as that hot fluid rises and then cools and then sinks back toward the core where it gets hot again, right? So it's going to heat up because that inner core is producing a lot of heat with those radioactive decay of those big elements that are happening. So the convection current happens when this hot magma rises and then it cools off when it's away from the core because the crust is much cooler than the core is, and it's going to then drop back down, making this convection current. Isaac.
How do undertows form?
So that's completely different.
Yes,
We
but
will
is it using a convection current?
No,
Okay.
what is a slab pull? That would be where the whole plate is being pulled, and sometimes they're pulled under other plates. So what we have right here, if you look at these pictures, what you have right here, this is a tectonic plate right here, and this is another one. And sometimes the whole thing is pulled under, and that's called slab pull. Yeah, great question. All right, so convection is going to cause movement in fluids. As they gain energy, they move. As they lose energy, they move. So warm air rises, it cools down, and it sinks. The same thing happens with fluid, with the magma that's down in the mantle. The warm magma rises up, cools down, and sinks back in. Let's watch a video where we can see that happening.
Today we are going to make a convection current. We are going to use liquid because it's easier to see than in a gas, but it's the same process. I have a tub of cold water here, and we're going to put a little bit of blue food coloring down here at the bottom. And I'm going to put a little bit of red food coloring in the middle. I have a cup of hot water, and I'm going to place that under the red food coloring. In a few minutes, we'll see the red start to rise up from the puddle at the bottom. There we go. See it starting to rise up? The red is starting to rise up. That's because it's being heated, and hot water is less dense than the cold water, so it's rising. Now what we're seeing here, see the blue starting to move in? This is exactly what happens in our atmosphere. As the warm rises, the cold moves in to take its place. So we see the blue moving in on the sides to take its place. There we have. The red continues to rise, and the blue is moving in and under to take its place. Now we start on this side, you're starting to see the blue, the cold, is moving in under the red current. And that's a convection current.
And that happens not only in the atmosphere, that also happens in the mantle of the Earth. So you can see here, we've got our outer core, our mantle, the convection current happens here. It happens like that. Okay, so I want to correct something that I said a few minutes ago. The outer core is solid, but that's not because it's cooler. It's because it's under pressure. I'm sorry, wait a minute. The inner core is solid. The outer core is more liquid because it's under greater pressure. So as we go down farther and farther and farther, we've got more and more and more pressure. We also have more and more heat. So just to clarify that, I think I said that the other way. But yeah, it is pretty cool. If you look at that, it's the temperature difference between the bottom of the mantle where it's near those decaying radioactive elements and the top where it's cooler. So remember, the deeper you go, the hotter it gets. And the farther out you go, the cooler it is. So the magma that's closer to the surface up here, see how they have it in blue? That's because it's cooling down. It begins to drop and it warms back up and then it starts rising up again. So we have this convection current, those circular movements. They're always constantly moving because there's always that temperature difference between the core and the crust. Now, look at this picture here. This picture shows the magnetic field that surrounds the Earth. Earth has a giant magnetic field around it, really a lot like a giant magnet. It's called the magnetosphere, and it's really, really important. So this has to do with the core. We'll get back to talking about it in a minute, but I want you to watch a video about why that magnetosphere is so important.
Our sun is constantly blasting huge amounts of hot plasma out into space. All those charged particles have a big effect on everything in their path. So what's protecting Earth from the solar wind and solar storms? Earth's thick atmosphere provides some defense, scattering and absorbing solar particles before they reach the surface. But our planet also has a secret weapon, a strong magnetic field it projects into space, mostly generated by molten iron alloys moving in Earth's outer core. The area of space where the magnetic field interacts with the solar wind is called Earth's magnetosphere. Its shape constantly changes as it's bombarded by solar particles. As positively charged protons and negatively charged electrons enter the magnetosphere, most of them are deflected around Earth, long before they reach the atmosphere. The magnetosphere really gets tested when big solar storms, carrying more plasma and traveling at higher speeds, are on a collision course with Earth. While most of the plasma is deflected, some of it gets trapped in the magnetosphere and funnels back toward Earth along field lines emanating from the poles. As charged particles from the sun collide with nitrogen and oxygen molecules in our atmosphere, they create the cosmic light shows known as auroras. The bigger the storm, the further from the poles auroras can be seen. Some storms are so big they interfere with satellites, cause planes to alter their routes, and can create other problems.
So if it wasn't for that magnetic field around the Earth, that magnetosphere, we'd be in trouble. All that radiation from the sun, all that heat would destroy the Earth. So here's the thing. Nobody is completely sure why Earth has a magnetic field. We know it does, but we're not sure why. The current theory is that it's because of the core. So remember, the outer core is molten. It moves around. It's so hot that the rock down there is molten. It's down below the mantle and it's above the inner core. Now, we think that there are convection currents in that outer core, but we think that the convection currents in the outer core are different than the convection currents in the mantle. Scientists think these convection currents in the outer core are what cause the magnetic field, but we're not sure. That has to still be discovered. We'll have to find that out. All right, now think about the layer of rock that's sitting on top of that moving magma. When you think about the fact that the mantle is molten and the crust sits on top of it, it sits on top of this molten moving magma, you can understand why there are so many different features of our crust and why it behaves the way they do. So they don't have poles. Yet some other planets have magnetic fields, not all. Some planets have magnetic fields. Let me find out which ones. That's a really good question. Which planets have magnetic fields? Mercury, Earth, Jupiter, Saturn, Uranus, and Neptune have magnetic fields. Venus and Mars do not. Yep, they do not. So there could be something different about their cores that makes them behave that way. Yeah, yeah, you're right. Isaac, Mars does not. What do you mean, Henry? They don't have poles.
Well, can they have magnetic fields if they don't have poles?
I'm trying to think that through. Can a planet have a magnetic field if it does not have poles? Is that your question?
Yeah, like how do they have magnetic fields if they don't have poles?
Okay, so a planet cannot have a magnetic field if it does not have poles, because the very concept of a magnetic field inherently requires a north and south pole. Okay, the next question that is, okay, so the thing is, all planets have poles, but they don't all have magnetic fields, right? So all planets have their north and their south ends. What's really interesting about Earth's too is that our magnetic fields, our poles have changed. And we can tell that. We'll talk about that a little bit more later, but that's pretty interesting. Valley, I know too. As soon as I hear that that we don't know the answer to something, it makes me want to do some studies and find out myself. So maybe one of you guys will discover that someday. All right. So again, think about the features of the crust that are because of that movement underneath. Think about what would happen if you took a bunch of pieces of foam and laid them on top of a swimming pool. How they would all move around, they would bump into each other, they would separate from one another. Well, the same thing kind of happens with the Earth. So the crust that is underneath the continents is different than the crust that's underneath the oceans. So we know that the crust moves, and we know that the crust is different. So the crust that's under the continents, isn't it nice when they name things so easily? Is called continental crust, and the crust under the oceans is called oceanic crust. What if the inner core was not hot? Well, it would cool down if the radioactivity stopped. Could that happen someday? Maybe. Maybe someday all those radioactive elements will have broken down into stable elements, and there won't be that heat generated anymore. That's not going to happen for billions of years. But maybe someday. Isaac.
Quick book suggestion, if anyone is wondering about any fiction books.
Your voice is kind of going in and out, Isaac.
Way better.
Yeah.
Okay, I put a book suggestion about Mars.
I'm sorry. What are you? I can't really understand what you're saying.
Can you hear what I'm saying?
Yeah, speak slowly.
Okay, I have a book suggestion about Mars.
Okay, let's hold that till the end, okay? Okay. All right, so some of the features that we see on the surface of the Earth. So name some. What are some of the things you see when you look at the surface of the Earth? There's a giant blue one on a globe. Helena.
The ocean.
The ocean, yeah. We see oceans and lakes and rivers and other big bodies of water. What are other things? Jasmine.
Mountains and volcanoes.
Yeah, mountains and volcanoes, which are mountains with hiccups, right? Mountains and volcanoes. What else? Maisie.
The ground.
Yep, we see the ground, we see the soil, the rocks. We see all the features of the crust. We see valleys in between those mountains. We see hills. So those are all features of the crust. We do see people, but people are not a feature of the crust. So that's you're absolutely right. We do see people. Now remember, the crust is not as hot as the mantle. The rocks that are on the crust are solid because they're not melted. They're not molten. And remember what rocks are made up of? What are rocks made up of? Come on, you just had rocks last week. What are they made of? Jasmine.
Minerals.
Yeah, rocks are made up of minerals. So some of the elements that we find in minerals are ones that you've probably heard of. Oxygen, silicon, aluminum, magnesium, iron, and calcium. Those are some of the elements that are in minerals that we have. Now, you guys remember what the thinnest layer of the earth is? Of all those 4 layers, inner crust, inner core, outer core, mantle, and crust, which is the thinnest? Aisha.
The crust.
Yeah, by far. And the crust doesn't have the same thickness everywhere. It's thicker under the continents and it's thinner under the oceans, but it's denser under the oceans. So think about what that means. That means it has more particles. Basically, the oceans have compacted the crust. So it's more dense, but it's thinner. And the land hasn't compacted the crust. So it's thicker, but it's less dense. You can kind of see that here. This is the crust under the ocean, and this is the crust under the continent. Part of that. Not a great picture. Now, the crust under the oceans is also different in the minerals that it's made of than the crust under the continents. The crust under the oceans has a lot of silicone and a lot of magnesium, while the crust that's under the continents has a lot of aluminum in it. So here you can see, if you take a look at this chart, you can see the elements that are found in the continental crust. There's more oxygen than any other element in the crust. It's about half of Earth's crust is made up of oxygen. Then silicon is next, then aluminum, iron, calcium, sodium, potassium, and magnesium. All right, now think about tectonic plates. We're back to tectonic plates again. So you guys said nobody had an answer for what tectonic plates are. Well, you're looking at them in this picture right here. The crust of our Earth is made of rock, but it's not one big continuous solid layer of rock. It's large pieces that we call plates. We call them tectonic plates. And it's because of these plates that we have things like earthquakes and volcanoes. Remember, all of these plates are sitting on top of that molten magma, so they can all move around a little bit. Now they're all touching each other, so they can't move a lot, but it doesn't take much movement in order for there to be things like earthquakes and volcanoes. Now, really what they do, those tectonic plates, they are division lines that divide the surface into pieces like a jigsaw puzzle. And each one of these jigsaw puzzle pieces is a little different size and a little different shape than any other one. They're different from one another. Now, all of those plates are made of the crust and the top part of the mantle. So they are rigid, they are hard, they are often called the lithosphere. Lith means rock. So they're the rock sphere. They're part of the earth that is made of rock. And both the crust and the top part of the mantle go into these tectonic plates. So here they are again. So take a look. You can see here, most continents like North and South America, right here, North America, South America, Africa, Australia. Most of them are just on one plate. But look at Europe. And look at Asia. They're both on the same plate. Some of the plates are little. Take a look at the Pacific plate right here. That's really big. The world's largest oceans overlap on different plates. The Pacific Ocean is over the Pacific plate and the Australian plate as well. This is all still part of the Pacific Ocean right here. So the Atlantic Ocean has 4 different plates that it sits on top of. It's got this one right here, the North American. It's got the African. It's got the South American plate, and it's got the Eurasian plate up here. All of these plates can move, and they can all have an impact on what we see on the surface of the earth. So find a plate, pick a plate right there that has both continent and ocean on it. Somebody tell me one. Drake.
The Pacific plate.
All right, let's look. The Pacific plate. So right here, we got a little bit of a continent on the Pacific plate, a little bit of North America, and all this ocean. And this is all still the Pacific plate too. Good, good, excellent. So the Pacific plate is a good example. Now find one that is completely ocean. Is there one that is only ocean? No, there's not. Maisie.
The Philadelphia plate. The one on the side.
The Philippine plate, this one?
Yeah.
Yeah, so it does look like it. You're right about that. There would be some small islands that are not in this picture that are on there. And if we look at this Coco's plate right there too, there would be edges of the continents of Central America that would be on there. Yeah, for the most part though, most of them are going to have both continent and ocean. All right, so Valerie says, how do the plates move? All right, that's where convection currents come in. They cause movement of those plates. So take a look at the boundaries. Where one tectonic plate meets another, in other words, where we have these black lines, there are boundaries. Do any of you guys live near a plate boundary? Kaylin, where do you live?
I live up in Alaska, so the edge of the plate literally goes along the islands of Alaska.
Yep,
And
right
right
there.
in that like tip right there, like that, that's Anchorage. So that's like 20 miles away from where I live.
All right, so yeah, you're very close. Anybody else live very close to a plate boundary? Drake, where do you live?
I'm like right by the edge of California.
So right in this area here. Yep, yep, excellent. So the lines show the plate boundaries, and look how close the boundary between the Pacific plate and the North American plate are to California. And look at how close they are to Alaska, where 2 of our students live. All right, so tell me which 2 plates meet near the middle of the Atlantic Ocean. Pick 2 that meet near the middle. Maisie.
The Africa plate and the Arabian plate.
So that would, the Pacific Ocean would be, oh, this would be the Pacific over here. I'm talking about the Atlantic right here.
Oh.
So you're right about the African, but then we could also say either the North American plate, the South American plate, or the Eurasian plate would meet there. Now, here's where they move. They move slowly and they move over very long periods of time. But because of that movement, several things can happen. And the arrows there are showing the direction that the plates tend to move. Right? So the North American plate tends to move in this direction. The African plate tends to move a little to the right and a little to the north, like that. Now, the things that can happen are either they can move apart, they can move together, or they can move sideways against one another. So that we call that divergent when they move apart, convergent when they move together, and transform when they slide against one another. All right, I have a silly little song that will get stuck in your head, but it will help you remember the way the plates move.
Convergent collide, divergent divide, and transform tectonic plate slide. Convergent collide.
Can you guys hear that?
Can you turn it up?
I
Not
don't
very
know why
well.
I'm not getting any sound. Huh, that's interesting because I'm not hearing any sound either.
I got a tiny bit. You have to like really boot your volume up.
Divergent divide and transform tectonic plate slide. Convergent collide, divergent divide and transform tectonic plate slide.
All right, I don't know why that sound is not coming out, but basically what it says is convergent collide, divergent divide, transform tectonic plate slide. Convergent collide, divergent divide, transform tectonic plate slide. All right, I'll see if I can find a better sound of that. It's worked in the past, but not now. All right, so here they are again. We have divergent divide, convergent collide, transform tectonic plate slide. Now, when they converge, when we've got convergence of their plates, sometimes one of them can slide under the other, and that has to do with density. So you can see that happening here. This plate is actually sliding under this plate right here. Same thing's happening here. This one is sliding under this one here. This one is sliding under that right there. So we call that process of sliding under one plate subduction. During subduction, one plate slides below the one next to it. Like, think of it this way. If you're having a war with your hands and your fingers are pushing against each other, eventually one of them is going to win. And it's going to go like this. One's going to slide under the other. Well, that same thing happens with tectonic plates. And when it does, that one plate that goes under, now it gets into the mantle. It's going under the cooler part and down into the very hot mantle. What happens to rock that's in the plate that goes down into the mantle? You guys know what happens to rock when it goes down into the mantle? Yeah, it melts. Exactly. It's going to melt. It becomes molten. It turns into magma. In this way, the rocks that were on that plate, all three kinds, sedimentary, igneous, and metamorphic, all three kinds turn into magma. If that magma cools down enough for that rock to solidify again, now we have igneous rock. That's one of the ways that the rock cycle makes all those different kinds of rocks. Okay, so if this is called subduction, the area where it happens is called the subduction zone. So remember, we learned that crust under the ocean is denser than crust under the continents. So which do you think usually slips below which? Which goes deeper in the subduction zone? Maisie.
The earth quartz, earthquakes.
The earthquakes are caused by some of this movement. I'm asking which one sinks below the other. Think about density. Which one was more dense? The denser one is going to sink below the less dense one. Remember, the denser one is the ocean. The water has made it denser and thinner. So in these subduction zones, when we've got a shore where we've got the denser ocean plate next to the less dense a continental plate, it's going to be the ocean one that's going to sink underneath. So what happens to the land on top of it? Or are tectonic plates separate than the land? No, the land goes right along with it. So that's how the rocks on the top go underneath. Now remember, this doesn't just happen like, you're not going to wake up in the morning and one plate has slid under the other in 100 miles. This is very, very small movements over very, very long periods of time. So it's always happening, but it's always happening slowly. In fact, you guys have probably heard that one of the oceans is getting a little bit bigger. like a quarter of an inch bigger every year and the other ocean's getting a little bit smaller. I believe it's the Atlantic that's getting a little bit bigger, but I'm not completely sure. I think I have that a little bit later here, but that's because the plates are moving. All right, so this is a pretty cool animation that shows how those convection currents move the plates.
It
There you-
happens because hot rock rises, heated by the Earth's core. Near the surface, the rock spreads in two directions and goes sideways. It begins to lose heat. Eventually, the much cooler rock sinks back down. Through this spreading process, the Earth's crust is very slowly dragged apart. And it's this that ultimately causes the continents to move.
You guys have probably, sorry.
Where the plates collide, the rock on the seafloor containing carbon from the dead plankton is carried deep into the Earth. As it descends, this layer of rock is heated, so the rock melts, releasing carbon dioxide. And gas is returned back into the atmosphere during an eruption. The remarkable cycle is complete.
All right, so that's pretty fascinating there, Meredith. Sorry to hear about that. I hope everything's okay. All right, so that's how they move. That's how the plates move, because the movement of the magma in the mantle causes them to move. Now, remember that the crust is thinner under the oceans and it's thicker under the land because the oceans compact it, press it together. Now, so the parts of the tectonic plates that are under the oceans are denser than the parts of the tectonic plates that are under the continents. That's why ocean plates go down. They subduct under the continental plates. Now, here's where we, remember I read you that cartoon at the beginning, It's My Fault? Well, these breaks or cracks that are in the Earth's crust caused by movement of those tectonic plates, those are called fault lines. So basically, sometimes the crust of the Earth can get cracks in it. And that happens because the rock that's sitting on top of the crust doesn't always move along with the tectonic plates. Sometimes the plate moves, but the rock underneath it holds still. Think of it kind of like a rug being pulled out from under somebody. Well, eventually the stress of those rocks just becomes too great and it'll break. And that's what happens. We end up having these cracks along there. That's when we say a fault line has occurred. So fault lines can be very large along plate boundaries. And the presence of one of these fault lines shows us that at some point in the past, those rocks were stressed and they cracked at some point. The problem is that could also happen again in the future. So where there are fault lines, scientists really watch for activity like volcanoes and especially earthquakes. They tend to happen along fault lines. All right, so you guys heard of Pangea before, right? Anybody heard of Pangea? Yeah. Pangea is where we think the planets or the continents were at one point. Now, there have been a lot of movement of plates over Earth's entire history, but the tectonic plates moving is what caused the continents to move in the direction that they have. And for those of you guys living in California, you live next to a really big fault. This red line right here is a giant fault. It's called the San Andreas Fault, and it's a big one. It's one of the reasons that scientists are always watching for any kind of activity in near the San Andreas Fault. All right, now, when we have these convergent boundaries, so they're coming together, think about what happens when one plate slides under another. It actually causes this top one to kind of bunch up a little bit. That's what forms mountains. Scientists call that uplift when a mountain is formed because the boundaries converge and push against one another. And then finally, we have these transform boundaries where one moves against the other. That produces earthquakes as well. But here you can see how divergent boundaries can create new ocean floor. We've got some magma that's coming up here through one of these fault lines where the two plates come together with one another, and new seafloor is being laid. So while it's going under in some areas, we're having new floor being built in others. New oceanic crust and mid-ocean ridges form in this way. All right, we're out of time for today. Anybody have any questions? You'll learn more about this in the lessons this week. All right, hopefully next week when I say, what's a tectonic plate, you can all tell me. Yeah, I don't know. All right, have a wonderful week, everybody. I'll see you next time.
Bye.
Bye, thank you.
Thanks for coming.
Bye.